Okay, today we're going to look at the hydrolysis of salts. Um, Now, this is a little bit of a complicated area for students. Tend to get a little confused with this because we don't think of salts. Remember, what a salt is really just an ionic compound. We don't think of ionic compounds as being acids and bases, but they can. Remember, go back to the definition of what an acid is. It loses a hydrogen ion, and a base is going to gain the hydrogen ion. So if we use those definitions, we can actually find a lot of things that are bases and acids that we typically don't think of. And here's where it comes from. It's based on the idea that weak acids are going to produce strong conjugate bases. Now, I'm putting strong in quotes here because they're not talking about these strong bases and these strong acids. This little chart here, it's in my notes that I gave you guys, really shows what I'm talking about. Here are those classified strong ions. So strong acids means that they 100% the associate into ions when they're put into water. So hydrochloric acid, nitric acid, sulfuric acid, they are going to completely ionize and lose the hydrogen ion when you put them in water. The strong bases would be down here, would be those hydroxides. Now there's other ones that are even stronger than that where you're really not going to see those. We typically stop right here with the hydroxide, and that would be your strong bases, sodium hydroxide, lithium hydroxide, when you put them in water. And again, 100% dissociation. Everything in between is considered weak. So if we look at hydrofluoric is in the weak category, but it's on the stronger end of that spectrum. All right, so what that means is it does lose the hydrogen ion, but not nearly as much as we do with the strong acids. Okay, so what that means is that if we look at this little fluoride ion, it means it's going to pull the hydrogen ion better than water will, is essentially what that is saying. So if I put this into water, water is going to attempt to pull the hydrogen ion from the fluoride to make the hydronium ion, and the fluoride ion would be remaining. But because the equilibrium only shifts to the right just a very small amount, less than 1%, well, maybe 3% or so, we find that most of this reaction lies or favors the equilibrium on the reactant side, not the product side. Hence why we have a Ka that is very low. Okay? Alright, so if that's true, what that means is that fluoride ions are good at pulling hydrogen ions, better than the water would be, because the water is our basis for the scale. And how I contrast that with chloride ions, which I'll do in just a little bit, the chloride ion is not going to be very good at pulling it. They're negligible bases, and that's important because these are going to be neutral, while these ions over here are going to be considered bases. Okay, so if I put the fluoride ion into water via something like sodium fluoride, lithium fluoride, or some sort of ion or some sort of salt, we're going to get the following reaction to happen. Okay, so that fluoride ion is going to go in here. So what we want to think of, if I'm talking about the major species, okay, if I put this into water, all right, my major species that I would have in here, my species would be sodium ion, because it dissociates into ions, a fluoride ion, and I would also have water. Now it's important to recognize this because you're going to see, okay, that's going to do nothing, as we're going to see throughout a lot of these problems, but that fluoride is going to react with the water, and we're going to actually get a basic solution. So if I dissolve sodium fluoride in water, there's no hydroxide there, we don't really see a hydrogen ion or anything like that, but what we do see is that it will react with the water just like the ammonia will, if you think about the ammonia reaction. So here's the little moral here. Conjugate bases from weak acids will form basic solutions. Okay, so keep that in mind. Basic anions are going to come from those anions from weak acids. So if I have HNO2, well, that's considered a weak acid. The NO2 minus is considered a base, right? It's the conjugate base of my acid that I have here. So whatever my weak acid is, my conjugate base would be a sufficient of enough base that it will react with water. HCN, my CN, cyanide ion, is basic. Okay, so any of these conjugate bases from weak acids are going to give us a basic solution. All right, so let's continue on here and look at the other ones. All right, now, just like we had our weak acids gave us bases, our weak bases are going to produce conjugate acids. And you can go back to the chart and look at that again. But again, what happens here is ammonia reacts with the water, produces the ammonium ion and the hydroxide ion. Now this here is considered a conjugate acid. Okay, it's a conjugate acid, and it will react with the water. It's stronger a stronger acid than water. As long as it's easier to remove the hydrogen ion from this than it is from the water, you're going to get an acidic solution to form. So when you have that ammonium structure, that hydrogen ion that's added to it, I know these are the hardest ones. I give you that. I know that these are really tough. So what you're looking for is ammonium chloride, ammonium fluoride, and where they really get confusing is when they give you these things here, where they have that CH3, NH2, actually NH3 plus. That's actually a base because it's the conjugate from that weak base NH, the ammonium, basically methylamine or methylamine. So that would be your base. So this is a base, and this would be the conjugate acid of that base. So again, it's considered a conjugate acid because it's acidic. So if you're looking at the bases, your acids that they form will always be considered, again, if it's a weak base. So these and again, the more weak bases you look at are ammonias and these methyl, groups where you have C2H5, NH2. That would be your base, and then you add the hydrogen. We'll look at those more in class. I know those are very, very confusing for everybody. All right, so again, ammonium with the water makes the hydronium ion and ammonia, and therefore we have our acid again. So we form an acidic solution. So again, the moral here is conjugate acids from weak bases form acidic solutions. So if we have things like NH4Cl, that is a 4 by the way, not a 9, that would be considered an acidic solution. It's going to make this solution acidic. Why? Because the major species that we have here would be ammonium, because it dissolves and dissociates completely, and we would get chloride, and you would have water. So this is going to react with the water to produce an acid. Okay, I hear you. I know these are confusing, but bear with me. We'll take a look at these a lot in the next couple days. We've got plenty of time to review them. Now, there's neutral ions, or anions, and there's neutral cations. And these are all going to come from your strong acids. So when you have strong acids, they produce conjugate bases that are extremely weak. As I showed you before with that chart, these are at the top. So these reactions lie very, very far to the right, no equilibrium. So therefore, this has no affinity or ability to pull hydrogen ions whatsoever. So the chloride ion is considered a weaker base than the water. Again, water is our basis for these. So when I add things like sodium chloride, lithium chloride, nothing happens. The chlorides will not react, right? So chlorides, bromides, iodides, nitrates, chlorates, perchlorates, okay, and HSO4 minus. 1, 2, 3, 4, 5, 6, 7. So these are your conjugate bases from the strong acids, from the 7 strong acids. These will always be neutral. They will have no effect on the pH. Okay, so if you've memorized those strong acids, you're in good shape because these conjugate bases from them will have no effects. Alright, so let's take a look at the opposite effect, which would be your, oh, I forgot the title on this one. Anyway, this would be your neutral cations. Okay, so neutral cations. And these are going to come from your strong bases. So strong bases, so that sodium ion, right? So if you memorized your strong bases, this would be your conjugate acids from these strong bases. Sodiums, lithiums, potassiums, calcium tends to be one, strontium is another one, and barium. So these would be those metal ions, those cations that are with those 6 strong bases you should know. And as you've noticed all year long, sodium ions, lithium ions, potassium ions aren't really going to do anything in any of these reactions. They're not going to do anything here. They're going to form neutral solutions. They are not going to have the ability to pull anything from the water. And this is a little harder because I can't really get into this because this is going into Lewis acids and bases. Metal ions are all considered acidic. Okay, these are just very, very, very weak acids, so they kind of have a negligible ability. But I can't really go into the reaction without going into Lewis acids and bases, and I won't do that right now. So just focus on these cations are always going to form neutral solutions. Alright, so if you want to, I would pause the slide or the video right now and write this down. Right, so here are those ions that I was talking about. Focus on the strong acids, strong bases. Salts form between these two. So if I have something like sodium iodide, if I have lithium perchlorate, okay, if I have calcium iodide, these are all going to form neutral solutions. Barium bromide, right? They're going to form neutral solutions because the cation does nothing. It's a conjugate acid from a strong base, has no affinity for anything, doesn't do anything, it's neutral, and this is neutral. So if I have any combination of these, always going to be a neutral solution. Okay, so make sure you keep that in mind. Again, how do you know that? Because you've memorized your strong acids and your strong bases. Alright, here's an example of ones that will form acids and bases. So anions from weak acids, okay, so that would be fluorides, sulfides, and there's a whole bunch of these, and there's too many to list, but what I would do is if I had something that was like sodium fluoride, well, that's going to be a base because that fluoride ion is going to react with the water. If I have something like sodium, no, let's not do sodium because I already did that. Let's do lithium nitrite. Okay, again, ignore that, focus on the anion in this case, those anions. That will react with the water to create the base. And this is what I was saying earlier. Really, the only one that you're going to see over here for the weak bases, or the cations from weak bases, would be the ammoniums and those organic structures with that NH, NH, NH in there. Okay, and here you're looking for the plus. Just keep in mind what's going on. We're looking at transferring hydrogen ions. Now, is it likely that this is going to lose a hydrogen ion and become an acid? Of course not. There's really not many hydrogen ions in here. Now, you could say this one might, but because it's negatively charged, it's going to attract the hydrogen ion, right? It will attract hydrogen ions. All of these are negative. The trick here is that if anything negative, anything that's an anion, is considered a base because it has the ability to pull the hydrogen ions in it. If it has an extra H plus ion in its structure, it has the potential to lose that hydrogen ion, therefore becoming a base, making the solution basic. Okay, I'm sorry, acidic down here, my fault. So it would make it acidic because it loses the hydrogen ion. It has the ability. It's not going to gain another hydrogen ion because if it gained a hydrogen ion, it's not possible because it's positive and positive. It's most likely going to lose it and not gain it. All right, so there's the background of hydrolysis of salts. What I'll do in the next video is I'm going to show you the calculations for this and take it from there. So thanks a lot.